Oh, hi, Mr. Wang.
You made it.
I'm sorry. I'm come back.
Did you get the message?
Stop being host.
Not yet. Okay, I'm going to stop my video. Okay, so we will continue on chapter 19. We will study the thermodynamics. As we know, thermodynamics has 4 laws. So the first law we studied in Chem 113 is about conservation of energy. And second law we studied last week. It tells us for a spontaneous process, the entropy of the universe increases. So this third law tells us where is the entropy is 0. It tells us the entropy of a pure crystal substance at absolutely 0 Kelvin is 0. Consider all atoms or molecular in the perfect lattice at 0 Kelvin. There will only be 1 microstate because perfect lattice limit all the atom or molecular at a certain spot. And also, if temperature is 0 Kelvin, which means there is no energy, so therefore there is only 1 microstate. So as that is said, so there is only 1 microstate, as we know W is 0. W is 1. So therefore, when you take the Ln1, you will get 0 for the S or the entropy. Okay, so this graph shows us the relationship between this entropy and temperature. You can see at 0 Kelvin, so the entropy S is 0, and this is the third law. The third law said for perfect crystal at 0 Kelvin, so the entropy is 0. So as you can see from this graph, as temperature increases, so those atoms and molecule gain energy, they start moving, so therefore they become random. Some of them moving faster, some of them moving slower, so therefore entropy increases. Then you come up to this phase change. So the phase change, the entropy will change very dramatic, increase dramatically, usually from solid to liquid. And then liquid heat up, get ready to boil. When the material changes from liquid to gas, so there is another dramatic change or very large jump for the entropy. Okay, so therefore we can define the standard entropies. The reference for entropy is 0 Kelvin, so therefore the values for elements are not 0 at 298 Kelvin, and not 0 watt. So this usually will be the unit for entropy. The standard molar this print, so we'll talk about entropy. So the standard molar entropy for gases generally greater than liquid and solid. It's especially true for the same matter, but be careful with size if we compare different matters. we'll see in the table pretty soon. If you compare H2 gas with benzene liquid, and even though H2 is a gas, but you consider 1 mole H2 gas with 1 mole of benzene liquid, and turn out the standard molar entropy of benzene is larger than the H2 gas. The reason is when the molecule are getting more and more complicated, which means they have more and more atoms, and then we know the atom can have a different arrangement, a different energy, different position, they vibrate, they rotate. So therefore, even though they are in liquid, they can create more chaos than those simpler atom or molecule in the gas. So standard entropy increases with molar mass. Standard entropy increases with number of atoms in a formula. Why? Because recall the so-called microstate. When you have more atoms in a molecule or in a formula, so there are more different ways to arrange those atoms. So therefore, there's more microstate. So this is the table part of those molar entropies for those selected substance. And you can see we can use them to do calculations. And so therefore, even for those elements, even for the most stable allotrope of the element, like oxygen gas and hydrogen gas, they are the so-called stable allotrope. And if you think about that H, formation entropy, so they are 0. But for the molar entropy, they are not 0. Another point you want to notice, as on the last slide, usually the gas material have a larger entropy, molar entropy as 0, but be careful with the size. You can compare this H2, as we saw on last slide, with this benzene C6H6 liquid. So even though this C6H6 liquid, but it has a larger number of entropy compared with this H2, because this molecule is more complex. So when you have complex molecular, and you can have more microstate. So therefore, even though in the liquid, it can have a higher molar entropy than some of those simpler substance, molecular, or atom in the gas. So more.
Okay, so will the liquid always be smaller than the gas?
For the same substance.
For the same substance.
Right, good. So good point, Roman. For the same substance, we will usually have this relation. We'll see this entropy or entropy S. So this S means entropy, and this S means solid. The solid entropy is smaller than entropy of liquid, and then is smaller than entropy of the gas. So this is true for the same substance. But clearly from this table, we can see if the substances are different, then you're not always true, or this equation is not always true. Okay, any other questions? All right, so therefore we can use what we just studied in the last couple of slides and compare each of those given substance, and then we can see who has in each pair who has a larger entropy, and explain the choice. Okay, so the first pair is NaCl solid. So the first pair is NaCl solid and HCl gas. So we have some other condition. Both of them have the same amount, 1 mole and 1 mole. And both of them have the same temperature, 25 degrees Celsius. So because how much we have are the same, 1 mole and 1 mole, temperature are the same. So pretty much will depend on the complexity and the state. So the complexity compare both of them, NaCl and HCl are similar. So they both have like 2 atoms, and so therefore we can treat this as a similar or same substance. So that we saw on last slide, Dorman's questions. So if for the same substance, the entropy in the solid state is smaller than the entropy in the gas state. So therefore, the first pair, this 1 mole of HCl gas should have a greater entropy. The second pair is 2 mole of HCl gas, 1 mole of HCl gas, and 25 degrees Celsius. So in the second pair, we compare the same substance, HCl gas, same substance, same state, same temperature. So what is the difference is how much we have. So obviously, if you have more molecular, so there's more random, more chaos, because those more molecular can have different place, different spot, and different speed. So therefore, the second pair, 2 mole of HCl gas should have a greater entropy. So the last pair, it compare 1 mole of HCl gas and 1 mole of argon gas at 290 Kelvin. And so again, we have the same state, same how much we have, they both 1 mole, same temperature, then what is the difference? The only difference is the complexity of those substances. So in argon material, there's only individual atoms. In HCl, this is molecular. So in a molecular, you have more freedom of motion. You can have vibration. You can have rotation. In atom, you clearly don't have vibration. So therefore, the HCl gas should have a greater entropy in the last pair.
Dr. Wang, for example, if we have a negative temperature, is that a higher entropy?
If we have a negative temperature, well, we will not have a negative Kelvin. Negative temperature. Well,
for example, negative 25 Celsius.
Okay. So if you have negative 25 degrees Celsius, so I think the principles for the temperature is usually as the temperature increases, the entropy increases.
Oh, okay.
Yeah. So
thank you.
Welcome. Yeah. So also, yeah, go ahead.
So that the more complex the compound is, the more entropy it'll have?
Yeah. Usually, if you have everything else are the same, they're more complex, and the greater entropy. All right. So then, how do we predict or calculate the entropy change? And we can predict the entropy change by doing a similar analysis as on the last slide. And we can also do a numerical calculation for the entropy change. So entropy changes for a reaction can be calculated in a manner analogous to that by which delta H, which means entropy change, is calculated, studied in chapter 5. So I changed this formula a little bit last night because initially I used delta S0, so that is wrong. So when you calculate delta S0, you will use S0. S0 will be given in the table. So those are so-called the standard. The 0 here means standard. Okay? So you are using those standard molar entropy. Usually you can find those from the table. So this equation shows us a way to calculate delta S0, very similar as you calculate delta H0. So there are a few more notations. So this means this Greek letter capital sigma means sum or add. And then what else is this n and m. So n and m are the coefficients in the balanced chemical reaction equation. Okay, so if we use this formula and we know our chemical reaction equation, and we can just look at the table, see what are the standard molar entropy, like the S0 for the product, for the reactant. Then we multiply by the coefficient, and then we can find out the delta S0 for the chemical reaction. Let's see one example is, so we have this one example. We have two H2O liquid split into two H2 gas and then O2 gas. Now we want to calculate what is our delta S0. So even before we calculate, we can predict what will be the sign for delta S. So we pretty much can say we start with liquid. We have produced three gases, so one gas O2, two gas of H2. We know our entropy S will increases, so therefore this delta S0 for this reaction should be larger than 0. So therefore, once you know the idea of your delta S0, you can do a calculation, then you can check at least check the sign correct or not. So to do the calculation, we just using the data from the table. On the quiz, on the exam, I will give you the data like that. You don't have to use really the textbook appendix C. So next, just think about the formula for the delta S0. It is given in this equation. And then you just substitute those numbers and read this equation carefully, see what are the coefficients and who is the product. So in this example, our products are one. Usually those coefficients has the name or unit mole. So when you see 1 means 1 mole, when you see 2 means 2 mole, and then these two also 2 mole. So therefore, what you do, you will see who is the product. The products are 2H2 and 1O2. And then what are the coefficients? Coefficients for H2 is 2, coefficients for O2 is 1. What are the unit mole? So therefore, we will use, let's say, 2 for one product, 2 more H2. And then we see for H2, this S0 is this. So therefore, we'll time this 130.58. Okay. And then what is the unit for S0 or S0? The unit for S0 is J over mole over Kelvin. So this is one number for the S0. And once you have those numbers, you can see the cancellation of some of those units. So in this calculation, the unit mole cancel out. Right. So remember this S means sum. You have to look at all the products. So this is only one product. The next product is O2. So the coefficient for O2 is 1 mole. So therefore you write 1 mole. Then look at the number for O2 is 205. What is the unit? Same unit, J over mole over Kelvin. So therefore this mole cancel out. Okay. So let's finish all the products here. And next you see subtract and all those reactants. In this case, we only have one reactant, which is H2O liquid. The coefficient for H2O liquid is 2. So when you say 2 in this calculation, you just give it a unit. You see the 2 mole. Then look at the table. We see the number as 0 for H2O liquid. Be very careful with the state. So that's liquid, and then 91, and the same unit, Joule over mole over Kelvin. And then we see again the cancellation, the mole and the mole cancel out. So that's the only reactant. Therefore, we finish this formula substitution. So therefore, we multiply and add. So what do we get? The first pair of numbers, when you multiply 2 with 130.58, you get 261.16. The unit is Joule over Kelvin. The second two number, and that's the trivial, so still have the same 25. So then these two number, 2 times 69.91 get 139.82 Joule per K. All right, so therefore we take these three numbers, add and subtract, and what you get is this number. Okay, so let's say this 3 number here, and give us 326.34 J over K. So that's it. So that's our answer. So therefore the answer is A. The answer is A. Is that reasonable? Yeah, the sign, at least the sign is reasonable. So we predicted our sign should be positive, and we do get a positive result. So it's our prediction, then our calculation. All right, any questions? Okay,
Dr.
good.
Wang,
Yeah,
what happened to the 130?
130?
Yeah, the 130.58. How did you get, did you not use it and then instead use 69.91?
We used it. So we see we here here, let me show you, Stephanie. So we see here we have 2 times this 130.58. So that gives us 261.16. See that?
Oh, okay. My bad.
Okay.
Thank you.
Welcome. Any other questions? Right. So we are going to change the format of our second law of thermodynamics. So remember our second law of thermodynamics, pretty much this equation. So delta S universe larger than 0 for spontaneous process. So we are going to change this second law and give us a new formula. To do that, we have to think about the entropy change in the surrounding. So why there's an entropy change in the surroundings? Because heat that flows into or out of the system can change the entropy of the surrounding. Right, so heat is energy. So when the surrounding gain heat from the system, there's more randomness. So therefore, the entropy will increases. Obviously, the entropy for the surrounding decreases if the heat go into the system. So we know for an isothermal process, which means the process happened at a constant temperature, we have this formula or equation. So the formula for isothermal process is delta S surrounding equals Q surrounding divided by T, temperature in Kelvin. And then we know the Q surrounding and Q system always has opposite sign. So therefore, delta S surrounding equals negative Q system divided by T. Now one more condition. We know at constant pressure, Q system is simply delta S 0. So therefore, we can calculate delta H for the system relatively easy. So therefore, we have this new formula for delta S surrounding. So delta S surrounding is actually can be calculated from some information of the system. So usually we can do that from those numbers in a textbook or in a table to get this information for our system. Then we can use it for our surrounding. So we will use this equation to modify our second law. Okay, so the entropy change in the universe. So that is a extensive property, which means it depends on how much we have or what we have. And we know the universe, as we studied in chapter 5, the universe, we can think about two parts. So one part, we call that system, and everything else is the surroundings. So because entropy change is extensive, which means the delta S universe equals delta S system plus delta S surroundings. Okay, so then from second law of thermodynamics, we know that for spontaneous process, delta S universe larger than 0. So we are going to change the format of this second law by using this equation, and then the other equation we just studied on our other slide, which means delta S surrounding for this guy here equals negative delta H 16 divided by T. Okay, so very simple. With this equation, and then we are going to change the way of this second law. So we write our delta S universe equals delta S system plus delta S surrounding. Then we'll substitute this guy by this formula. by this formula. Okay, so what that means, we will keep write delta S universe equals delta S system plus this number. So instead of writing this number, we'll write this guy. So you are seeing this on this line. Okay, you can see here, you can see this substitution. So what happens is you still have this delta S universe. So delta S universe equals delta S system equals delta S system. Now plus delta S surrounding become minus delta H system over T, because we know delta S surrounding equals negative delta H system divided by T. Okay, so next, what you do, you just multiply this equation, both sides by negative T. So as we said here, to multiply both by negative T. Okay. So we will take this left side, multiply by negative T. And then we take this right side, multiply by negative T. Okay. So the left side is simple, so that becomes negative T times delta S universe. Then on the right side, we will distribute. So we take this negative T times that. Then we take this negative T times this. Okay. And what you get, so you will get negative T times delta S system. So that you get from this distribute. And then from the second distribute, so negative T will cancel out this T, and negative sign here with this negative sign here become positive. So therefore that becomes simply positive delta H system. Okay. So therefore we summarize what we get after we multiply this equation by negative T on both sides, we get this. Okay, any questions? All right, so once we can get this, and you can rearrange. So here you write the plus delta H here. You can move that around. You can write that first. So just, so this line, nothing really happens. Just you write this one first, then write this one second. Okay. So then you will name them. Okay. So what do you name this guy? Okay. What do we call this? So we call that. We call that. So everything I circle in red, delta G. So just give that a new name. Okay. And then delta G is the so-called Gibbs Free Energy change. So G is Gibbs, or Gibbs Free Energy. So delta means change. So therefore, we have this new formula for the delta S universe. So therefore, we get delta G equals delta H minus T times delta S. And we are going to use this equation a lot in this class. Okay, so remember the second law tells us for a spontaneous process, delta S universe larger than 0. And the temperature in Kelvin always plus. So therefore, we have this negative sign in the definition. So for a spontaneous process, delta G will be negative. For a non-spontaneous process, delta G will be positive. For an equilibrium process, delta G equal to 0. So therefore, we have this new way to decide whether the process or a chemical reaction is spontaneous or equilibrium. So if delta G is negative, the forward reaction is spontaneous. You can see in this diagram, if we have this chemical reaction, so on this side, you only have those pure H2 and N2. On this side, you will have the pure NH3. And here you will have N2 and H2. So we know this equation, this chemical reaction is equilibrium. So to understand or to explain this diagram is, you can say, if you have only N2H2, so what is your Gibbs free energy? What is the free energy here? What is the G? You can see the G in this diagram. So here is the G. Yeah. So this delta G is negative for spontaneous, which means the G kind of a gravitation, even though that really the G means Gibbs. So it's kind of, you have a higher potential energy, and naturally it will go down, so therefore spontaneous. So therefore, before this equilibrium point, and if you have a lot of reactant, you will produce the product. So therefore, the forward reaction going from N2H2 to NH3 is spontaneous. Once you have here, and you will have that delta G, can just on this little point here, so delta G becomes 0, and here delta G less than 0, and here delta G more than 0. So that's how you say this in terms of the delta G or G. If you think about the Q and K as we studied in chapter 15, so in chapter 15, you can also use Q and K to predict the direction of the chemical reaction. And as you remember, if Q less than K, your reaction was shifting from left to the right to increase the Q, so therefore you will get Q equal to K. Oppositely, if Q is more than K, you need to decrease the Q in order to get Q equal to K. Therefore, you're going backward. All right. So you can also here in this chapter use delta G. So use compare Q with K in chapter 15. And here you will use delta G to the predictions. Okay. So this is the 3 points you want to memorize when you're using delta G. So when the process is spontaneous, when is the process at equilibrium, when is the opposite process spontaneous. All right. So this example is calculate the standard free energy change for the formation of NO from N2 and O2 as in this equation. What given to you is delta H, so this is given, and also delta S. And then once you find out the standard free energy change, which means delta G 0. So once you find out delta G 0, just see the sign of delta G 0. If the delta G 0 is less than 0, or delta G 0 is negative, then we know this reaction going from left to right is spontaneous. Otherwise, if it's 0, that means equilibrium. If positive, that means going reverse is spontaneous. So to calculating this delta G from this delta H, delta S, just using that formula I highlighted in blue, we call that equation 19.12. So this equation. So we are going to use this equation together with the given delta H, delta S, and T to calculate delta G0, which is kind of straightforward. Just be careful with the unit. Okay, you can see here, we have this delta H is a kilojoule, and our delta S is joule. So the K is okay, so K will cancel out after you multiply this delta S by T. So the problem is you will usually forget to make the unit are the same. So you decide, or if the multiple choice question, all the answer is given in kilojoule, you want to change them into kilojoules. If the multiple choice question are given to you in joules, you change both of them into joules. Right? So now let's see for this problem, and we can do either way because that's not a multiple choice. So we rewrite our equation for delta G equals delta H T times delta S, and then we change them into both of them into kilojoules. So we just use this number for delta H. So this number becomes this. So probably let me highlight. You can see them relatively easy. So where this 180.7 come from this given number here. We keep this kilojoule, okay? So this will finish our first term. So delta H here becomes this number here. So the second term, okay? So we call them term. So this is our first term. So altogether here is our second term. So the second term, in the second term, what you have is this negative sign from the formula. So write negative sign here, and T in Kelvin. So make sure if not give you in Kelvin, so this give you Kelvin, so that's good. If I give you not Kelvin Celsius, you change the temperature in Kelvin. So make sure there's Kelvin, and then we have the other given delta S. So delta S here. So delta S is J over K, so K and K cancel out. You cannot add in J with Kj, so you have to do the conversion. So you have to use this conversion to cancel out the J here and get kilojoules. So now you can add, multiply, and add. Okay, so you still have 180.7 kilojoule. So 298 times 24.7 divided by 10 to the positive 3 or 1000 to get 7.4. So this negative sign still this negative sign. All right, so we get this number for our delta G0. Okay, so once you get the number, also the sign for your delta G0, you can use the sign of delta G0 to predict the spontaneity of your chemical reaction. So we have a positive delta G0. That tells us what? That tells us what about this chemical reaction. So this chemical reaction as written going from left to right. Is this process going from left to right spontaneous or non-spontaneous?
Non-spontaneous.
Good. So why is non-spontaneous? Because delta G is a positive number. So when delta G is a positive number, your reaction going from as written from left to right is non-spontaneous. All right, questions or comments?
So it's G is less than 0. I'm sorry, G is greater than 0 because it's going from two of them to one product, but it's good.
Yeah. So very good, Roman. So that means as we calculated for this reaction as written, going from left to right. So that's how we calculated the delta G. So we get this number larger than 0. So therefore, going from left to right is non-spontaneous. But you think of the opposite. So if you think of this product and decompose into the two reactants, then that becomes spontaneous. Is that right, someone?
Yeah. Thank
Okay.
you.
Welcome. So forward reaction is non-spontaneous, and the reverse reaction is spontaneous. All right. So there are different ways of calculate the delta G. So delta G obviously is very important because if we know that, we can predicting the spontaneity, and also if we know that, we can calculate our equilibrium constant. So we just learned one way to calculate delta G by using delta H and delta S. Now there's an easier way to calculate delta G. But this easier way will have some sacrifice because in this way, you can use this number in the table, but you can only calculate for one temperature. So whatever this number give to you in the table for that temperature, then your delta G is at that temperature. But if you use the equation on the last slide, you can calculate delta G0 at other temperature other than the temperature specified on the table, approximately, but at least approximately. So what you do, if you want to use this similar way to calculate delta G0, you just go to the table to find out this guy, so this number, okay? So this number, and also that delta H0F, that number, then S0, this number. So usually this three number, so this three number is given in some tables. So in our textbook, it's given in Appendix C. So you can do a very easy calculation to get delta G0 by using delta G0F. You see the difference? You want to get this guy. So this guy don't have a F. So you use those F, pretty much all look similar. So delta G0F, delta G0. So use those F means the formation in the table to calculate delta G0. So similarly as when you calculate this one, or when you calculate delta S0, you will see this means sum. So this means sum. Then this N and M are coefficient. Okay, so another notation is this 0. Sometimes we call that not. So this represent standard state. So what do we mean by standard state? A standard state Means if you have in your process, if you have some solid, your solid should be pure solid. If you have liquid, it should be pure liquid. If you have something in your process, the gas, then the gas pressure should be 1 atm or 1 atm partial pressure if you have a gas mixture. If you have a solution, you should have 1 molar, and then element should have some of those element format should have delta G0 F equal to 0. Well, we know this concept for element, so called allotrope. So one example for different format of the same element is carbon. So we know carbon can be graphite, can be diamond, or maybe can be carbon gas. So those are all elemental format for carbon. So then what format of carbon will have this guy equal to 0? So this delta G F 0 F not equal to 0. You usually will know the most stable allotrope, like oxygen should be O2, carbon should be graphite. So if you don't know, just looking at the table, see which one has this 0. So whenever the format give you delta G0F equals 0, so that will be the most stable allotrope. Right. So this example is using the data from appendix C to calculate the free energy change for this chemical reaction. I think at this temperature. So for this question, obviously you can use a TDS with delta H0, delta S0. But here we will use delta G0F, so relatively easy. You can see why it's easy. If you use the first approach, you have to do like 3 calculations. You have to find out what is this number, what is this number. Then using the formula delta G0 equals delta H0 minus T times delta S0. So you have 3 calculations. If you use this, you just do less calculations. So if I give you those numbers on the test, you want to use an easier way, just using this one. So the formula will be like what we saw on the last slide. And here just a few more explanation. You can see this guy obviously the compound, so this should not be 0. So this is the compound. So therefore, that's not 0. That's reasonable. So this is the element, and this also element. So why one element is 0, the other element not 0? This is what we studied on the last slide, because some elements have a different format or allotrope. So the P4 gas is not the most stable allotrope for phosphorus. So therefore, this is not 0. But for chlorine, so chlorine gas or Cl2 gas, the most stable element, most stable allotrope for chlorine. All right. So after we feel understandable for those numbers for the delta G0, then we keep in mind we need this equation balanced, because we have to know what are the coefficients. Then we're just using this formula, right? So you can see this 4, from this 4 for the product, we're adding this unit mole. So we add on this unit. In the coefficient, you don't have a unit. So here, no unit written. So even though no unit written in the equation, we know those coefficients can have two possible units. So these for either mole or molecular. So in this case, we use moles. All right, so you will take 4 times the number for this product. So then 1, so this 1 here, okay, times this number for P4. So that one is 6 times 0 is still 0. So 6 for Cl and 0 for 6 for Cl2. So Cl2 still 0, therefore still 0. So you multiply and add or subtract, you get this number. And then obviously we get a negative number. So that means the reaction as written going from left to right, it is spontaneous. Just to remind us.
Why is PCl3 negative?
Why is PCl3 negative?
Yeah.
Okay, so that's good question. I think that means this guy, this number from equation, this equation what it looks like from, so P is probably solid. I think the phosphoria have different solid. One solid is solid white, the other one is solid red. So solid white will be the most stable. So you use the most stable element and then write up the equation. So you need Cl2 gas, then produce the PCl3 gas. So what you do, you will write this so-called formation equation for the PCl3. Okay. So once you have this formation reaction equation, you can measure what is the delta G 0. So you measure this delta G 0 equals this negative 296.6. Okay, and then you put that in the table. So therefore here we use 269.6. So that's not really tell you why, but just basically you get this number for this PCl3 from the table. Then how they get this number from the table? They just measure this chemical reaction. Okay, so then this chemical reaction is formation reaction. So therefore this delta G will be delta G0F.
Okay.
So that kind of, yeah. So that kind of tells us. Okay, Madison, just a minute. I saw you raise your hand. So that tells us to produce the PCl3 from these two elements, it is spontaneous. Is that clear? Okay, I saw Madison raise your hand. Madison, go ahead.
Okay, so why are we subtracting? I thought we were supposed to add the reactants together, like we're doing the sigma.
Good point. Good point. So if you let's say if you use our subtracting, so adding, so therefore this, so let me put this parenthesis here, then this add, right? So then you just distribute this negative sign, because if you either you add them together then subtracting, or you just subtracting them individually.
Okay, thank you.
You're welcome. Okay, any other questions? Right, and so the second part of the question is if we get this negative 1102.8 for the forward reaction, then what will be the delta G for the reverse reaction? Well, that is the kind of you think about how we calculate the delta G. We calculate the delta G by using the product minus reactant. So when you reverse the reaction, So your product become reactant, your reactant become product. So therefore, pretty much you reverse everything. So therefore, you will reverse the sign. So if we get negative that for the forward, so for the reverse, so this is our forward reaction, and this is our reverse of the forward. So obviously for the forward, we get negative 1102.8 kJ. So delta G 0 equal to that, and the reverse opposite. So that's probably a very good question. So next, we can use this formula and just analyze the sign of delta H, delta S. Then we can have some of those reaction characteristics, right? So keeping in mind, so the Kelvin temperature always plus, because we never have a negative Kelvin. So this negative sign here from the formula. Then altogether this negative T times delta S. So this guy called the second term. So the second term altogether this negative together with T together with delta S can be positive, can be negative, depending on the sign of delta S. And then delta H just tell us the chemical reaction is endo or exo. So now if we see our delta H is negative, and we see this positive for this, and then you can see this second term will be always negative. So let me change here. So here the plus, and here the negative. Here the plus on the first. So plus T plus delta H plus delta S. So therefore this is negative. So therefore, if you are negative this, then and then another negative from the second term, so your delta G always negative. So your delta G is also negative no matter what is the temperature. So therefore, it's always spontaneous for the forward reaction. So one example is ozone decomposed into O2. The second scenario or second possibility is the opposite. So what if we have our delta H positive? So we have this delta G equals delta H minus T times delta S. So if this is positive, and then this is negative, T is always positive, then you minus the negative numbers to have plus. So what you get is plus and plus. So plus plus always plus. Therefore, it's always non-spontaneous. So obviously that's what is the opposite of the first reaction. And then these last two cases, so if delta H, delta S have the same sign, negative, negative, positive, positive, then that will depend on the temperature for our delta G will depend on temperature. So one possibility is delta H negative. So if our delta H is negative, so that means our delta G will equals a negative number. Okay? Then this guy together, let's see, we have a negative, let me write here, negative T times delta S. So if this is negative and this is plus, there's another negative, so therefore that will become plus. So therefore what you have is a plus here. So then you have this sum, so they are not multiplied. So you have a negative sum with a plus, then the result may be negative, may be positive, depending on who is bigger. So obviously, as the temperature increases, this plus is getting bigger. As the temperature getting lower, this plus is getting smaller. So therefore, if this is smaller plus with a lot of negative become negative. So therefore, this will be spontaneous at lower temperature. All right. So obviously, you will have a spontaneous at high temperature. So these are two examples. So any question about this analysis of this table? All right. I think this is about this example. We probably have finished this example because we were interrupted by the internet, and then we'll continue later. We'll finish this example first. So what is this example? This example is about, without using data from that, predicting whether this delta G is more negative or less negative. So what you do, you want to use this equation, delta G equals delta H minus T times delta S. So you have this negative delta H, then the question is delta G more negative or less negative than this delta H? It will depend on the sign of delta S. So then let's predict, even before we calculate what is the sign for the delta S. So we can see we have 1 gas here, and 5 gas here, and then 3 gas here, and 4 liquid. So we have less gas, so therefore for this chemical reaction, our delta S should less than 0. So therefore delta S is negative, so T is always positive. So therefore negative with negative, so altogether this is positive. So therefore your delta G will be delta S. So delta G0 will equals delta S. I don't want to use plus, I want to use sum. So delta H sum a plus number, so therefore become less negative. So you are adding a positive number. Any question about the first part of the question?
So the right side is bigger because it has more gases. Wait.
The left side, yeah.
The left side.
Yeah. Okay, so we're predicting our delta G will be less negative than this one. So this delta H is negative, okay? So we predicted our delta G will be less negative than this, maybe negative 1,000, maybe negative.
Sorry, can you go over this again in the beginning of next class, part A?
Okay, Tessa, yeah.
Sorry.
Okay, so we'll do that, and then let's see the next, the part B is calculate, and that will be trivial. So what you do, just using this. Okay, so if you for the part B, just using those numbers, that's using an easier way to calculating delta G using delta G0F, and so you multiply, subtract, you get this number, and you can see here this number is negative 2100, and for delta H negative 2200. So therefore, delta G it is less negative than delta H. Yeah, so we'll stop here. As Tessa said, we will go over this part A and next class. So before you go, probably let me give you like one proof question. And okay, so how you respond? I think if you see that, you probably can click on that.
Yes.
Okay, you can click on that. Okay. So I will. I say I have 2 responses.
So if it was negative and close to 0, would we call it negative or close to 0?
If you think close to 0, say close to 0. Yeah, so you have 2. As you adding them together, you have 2 gas on the right, 2 gas on the left. So you have a similar amount of gas on the left and on the right. So there's not too much change. You don't have too much. You don't really increase a lot of gas. You don't really decrease a lot of gas, pretty much you keep like constant. So therefore, the entropy does not change too much. Just feel respond to this question freely. I will give you the credit anyhow. So I'll give you 1 credit for the attendance. Remind you, when you submit the practice question for chapter 19, you don't submit like the picture or the PDF. Just go to take the quiz. Right? You know where to take the quiz on Canvas.
Dr. Wang, are the questions on Canvas for the extra credit, are they the same as the ones that we would have had to submit, or are they completely different?
Yes, they are exactly the same. I did not random the answer, so you will see them exactly as you get from the Canvas. So just practice on those questions. So as you are ready, just go to on Canvas and just take the quiz as the submission for your practice question.
Okay,
So
thank you.
yeah, you're welcome. Yeah, so the quiz question exactly as those practice questions you can get from Canvas. So just keep practice. So give you a good way to practice for the exam 3. So once you know how to do those questions for the practice question, then just take the quiz. We will use a similar question on the quiz as I give to you on the Canvas. Actually, exactly the same. Okay, now again for this proof question, you can see your reactant is N2 gas plus O2 gas equals 2NO. So you have starting with 2 more of gases and you ending with 2 more of gases. So you don't have too much change on the entropy S. So delta S do not really change too much. If you don't have too much change, you probably don't have to say the positive or negative. So you just don't have too much change.
Bye, Dr. Wang. Have a good day.
Bye, Danya. Yeah, so if you have not bye, just click on the pool on your screen, and you will see this pool question as you saw on my screen. Click on the polls on your screen, and then click on those choice on your screen.
Bye.
Bye. Okay, so I will be here for the office hour. If you need help, just come back in from 10:30 to 11:30. Have a good day.
Hi, Dr. Wang. Have a good day.
Bye. Have a good day.
Bye, Dr. Wang. Thank you.
Welcome, Stephanie. I can recognize some of your voice. Okay, so the correct result is close to 0. I think most of you get it right.